So good morning, everyone. Welcome to this third lecture of Memory Design and Test course. And let us start with a quick review of what we were doing in the last class. So who will tell me what were we doing in the last class? Yes.
So we were studying about different types of memories.
We studied about different types of memories. We looked at
Some
volatile memories, non-volatile memories, and what kind of volatile memories, even in the category of volatile memories.
Random access and non-random access.
So can you give some examples of non-random access memories?
FIFO, LIFO, shift register, and CAM.
And CAMs.
Yes.
Okay. And
CAM.
yeah, what about the non-volatile memories?
Sir, EEPROM and EEPROM flash.
So why are we talking about also all these types of memories? Where are they used?
So like RAM is used in our phone, also in our computers. Flash memory is used for pen drives, and different types of memory have their different kinds of applications.
For suppose shift register will be using it when we have a latency issue, and FIFO will be using when we have a frequency issue.
Okay. So we saw that FIFOs are used also in synchronizers. And anyways, wherever we want to implement
Sir?
Faisal, you want to say something?
Sir, I have a doubt from the previous class. Can I ask right now?
Yeah, let's do a quick review. हो सकता है उसी में resolve हो जाए.
Okay, sir.
So what was the next thing after looking at different kinds of memories? What was it that we looked at?
Various parameters.
Architecture of memory.
A top level architecture of a memory. So what does a top level architecture of a memory include?
Control, decoder, memory
the
array,
decoders, the control, the memory
state
array,
cell, sense amplifier, write driver, input output interface,
input outputs, yeah, input output buffers, and all that. So this was what we were looking at in the last part of our class. What did we say? We said that the clock generates internal clocks, which lead to decoding, of addresses and selection of what we call as a word line. When the word line is selected during the read cycle, a differential will appear across the sense amplifier nodes, and then we would kind of latch the output of the sense amplifier and push the output onto the Q bus. For the write cycle, we said that it would again be same kind of decoding initially. Word line would be selected, but even before word line is selected, we would have a word line clock, which would kind of discharge one of the bit lines on which we wanted to write a 0, and we would do the write operation. So this was what we discussed in the last class. Any questions around it now?
So I have a question about the FIFO part that we have discussed. Like we were saying, when the data transfer rate is equals to or less than the data receiving rate, then the FIFO is useful to us. But if the data transfer rate is greater than the receiving rate, then FIFO is of no use. So I was not able to understand that part.
Okay, so then the FIFO would not be able to help you in a significant way. So we discussed about an example. Suppose, let us say, Faisal, you have a bag.
Yes.
Suppose you and Vaishnav, both of you, you are interacting with each other. Vaishnav is speaking 100 words per minute.
Yes, sir.
But you can understand only 50.
Okay.
Now, whether I put a interface in between which would slow down Vaishnav's words as they reach you, will it help? Because after 1 minute, what happens? Vaishnav would have spoken so much more that you will need 10 more minutes to just decipher what has been said.
Yes, sir. Yes.
So that is where FIFO fails, because FIFO capacity is finally limited. If there is this high frequency transmission from one side and a lower frequency acceptance from the other side, FIFO cannot work. FIFO cannot help.
Yes, sir.
Is this clear now?
Then we have to increase the frequency of the receiver. Or
Yeah. Then either
the
you
frequency.
increase your capability to accept words from Vaishnav, or Vaishnav starts to speak slowly.
Okay. Okay. Understood, sir. Thank you.
Yeah.
Sir,
Vaishnav?
Sir, the sense amplifier enable signal, sir. Is that generated by clock or is that generated by something else? Because in
we'll look at it later.
right clock.
Very good question, Vaishnav. We will look at it later. We will actually talk about it in, I think, 7th or 8th lecture, 9th lecture.
Okay, sir. Okay. Thank you.
Okay. Yeah. Animesh, you wanted to say something?
Yes, sir. The same case Faisal was talking about. I thought depth of the FIFO comes into picture only when we have a slower acceptance than our write speed. Then only the depth of FIFO would come into picture, right? If the difference is more, I will need a more FIFO depth, so that I can buffer all that writing. And I can obviously decipher it in later stages, idle cycles.
Yeah, yeah. So if there are no idle cycles, that is when FIFO would fail.
Yeah.
Hmm?
Okay, sorted.
Okay.
So what is desired when there is mismatch in capacity?
I'm sorry?
Whether we increase the slowing frequency? Hello?
Yeah, yeah. So if you slow down the frequency, what happens? If suppose Vaishnav starts to speak slower.
Yeah, I think I want my slower system to respond faster.
Okay, so if you improve, because Faisal was asking the question, if you improve Faisal's ability to accept more words per minute, then also something can improve. But finally, if it is a continuous transmission from Faisal's side, from Vaishnav's side, and Faisal cannot accept it at the same rate, however big a FIFO you put, it will not help.
Yes, sir. Yes, sir.
Hai na?
Agreed.
Okay. So again, don't get too much digressed by it. This course is not about designing synchronizers. We're discussing this because, okay, this is one application of FIFO and it is an interesting application of FIFO. We also have a paper around it. If you look at my Google Scholar profile, you will also find a paper around this kind of cross-bus synchronizers that we have worked on earlier. Okay. So now, is it okay if we move forward now?
Sir,
Any further questions from the last class? Yeah, Mohan.
Sir, I have one question. Like for each bitline, we need one sense amplifier, right?
No, not necessary. For each, there has to be some sense amplifier associated with every bit line, but for each bit line, we need one sense amplifier. I never said that.
Okay, and so my thought was we are taking the output from the sense amplifier to mux, and then we are taking only one bit data, right? So can we do reverse? Like first we do the mux, and we can use only one sense amplifier.
Yeah. So did I say that we will put a sense amplifier on every bit line and then do a muxing? I don't think I said that. In fact, that is, as you are suggesting, Mohan, that is how it is usually done. That is why I said every bit line may not have a sense amplifier. We may first mux the bit lines and then we have a sense amplifier. That is a typical implementation. Okay. In a DRAM though, every bit line will have a sense amplifier. Should we move forward now? Any questions? Okay. So now let us look at the signal flow in terms of timing diagrams. We said that clock comes, clock leads to generation of what is called as CKI and CK internal. Okay. In a little while, after decoding happens, then we will generate what is called as word line and reference word line. And on the IO side, we will generate a write clock. The same signal that I kept as W clock in the previous slide. When the write clock gets selected, what happens? Bit lines, because the write driver would do something, one of the bit lines would discharge. The other bit line will remain at 1. The reference bit line would also discharge. And after the word line / reference word line are generated, what happens? We generate a signal which is called as write detect, which kind of senses that the contents in one reference cell have been written. After write detect is received, we generate a reset signal. After the reset, so yahan tak abhi humne dekha tha, we had done until write operation getting completed in the previous slide. Now I'll be adding an additional step of reset. Once we know that the sense amplifier has operated, once we know that the write detect has come, once we know that the memory operation, the intended operation of this particular cycle has been operated, memory itself generates a reset internally. Okay, so this is true for almost all the embedded SRAMs, even DRAMs, even flash. So this is called as self-timing. Means that memory times itself and tells now I can reset the memory, like I can now be resetted. So why is it important? Because now I am not dependent on external clock's duty cycle. The external clock frequency does not impact my memory operation. Let us see why this is important. Now, after this reset comes, what happens? The clock internal is reset. Subsequently, word lines get reset. Bit line is pre-charged. And after the bit lines are also pre-charged, everything is done. Write detect goes down and reset goes down. Okay. Now your memory is all ready. This was the initial state. The state and the initial state are the same. Are you able to see this? Now your memory is ready to accept the next clock edge. Now, why is this sequencing important to be kept separate from external clock? Any ideas? Ranjit, you have a question.
Sir, firstly, I didn't understand what is this internal clock.
Okay, we will come to that. Anything else?
And then what is the difference between the reference word line and the word line? And what is the difference between the bit line and the reference write bit line?
Okay. Anything else?
That's it, sir.
Okay. So any other questions? So everything else is clear, huh? Okay. So Ranjit, the question that you posed actually has the answer to my question in itself. We do not use external clock for generating all the internal signals. There are two reasons behind it. One is that internally, the clock would need, inside the memory, the clock needs to go to numerous places. We said that the clock would go to all the row decoders. We said the clock will go to all the IOs. You see, we talked about that there is a write clock that has to go to the IOs to activate the write driver. We said there is a clock that goes to the row decoders to activate the row decoders, word line generation, and so on.
Yes.
So if we use the external clock to do all that, then the total load on the external clock will be humongous.
Okay.
It is absolutely unacceptable. For any IP, whether it is a memory or a PLL or a standard cell. So we talked about standard cells in the previous course, but I'm saying even PLLs, ADC, DACs that you may do in mixed signal courses, even for those, the input capacitance of any pin has a limit. You cannot keep that input capacitance beyond a particular threshold. For some technology, it could be 10 femtofarads. For another, it could be 25 femtofarads. For some, it could be 30 femtofarads or 50 femtofarads. But you will see there is always a limit. Okay. And if you travel clock throughout the memory the way we need it to be traveled, that capacitance would go so high that this would not work. So you somehow need to buffer it, and somehow you need to generate some internal clock. Okay. So does this part help? That there has to be some buffering, something which is internal to the memory and not the external clock.
Yes, sir. Yeah.
Now, when we are generating this internal clock, we want to do something else. We want to say that, see, now memory, for that matter, you will realize as we proceed that the memory read operation and write operation can be very slow, which means that you want to keep the word line on for a significant amount of time. And the remaining reset operation can actually happen very, very fast. So the low period of the clock need not be very high. So you want a very long high period of the clock with very small low period of the clock. That is what the memory requirement is. However, when you talk of a PLL, what is the typical duty cycle you would want it to operate at? A typical clock generator, any clock signal that you would have seen, any oscillator, what does it do? It says almost 50% high time, almost 50% low time. Is it not the case?
Yes, sir. But
Yes,
in
sir.
this, it should be high, greater than.
So, yeah. So now let us take the example that my memory needed 2 nanoseconds of high period and 0.5 nanoseconds of low period. So in fact, totally my memory could operate in 2.5 nanoseconds, let us say. That is the fastest speed at which memory could operate. Can we say this? Now this is a hypothetical case and this is too much simplification also. Okay, but let us say that in total 2.5 nanoseconds the memory could have operated, of which 0.5 could have been low period and 2 could have been the preferred high period. That is how my word line wanted it to be. Let us say that. However, if the clock generator's duty cycle is 50%, what will be the frequency? What will be the time that the clock generator will take? 2 nanoseconds for the high time, because that is what is required. And because this is 2 nanoseconds, the low time will also be 2 nanoseconds. So the clock frequency will now be 4 nanoseconds. Are you able to see this?
Yes, sir.
So what has happened? Even though I could operate at 400 megahertz, because I did not have an internal clock, I said my external clock will be used internally to the memory after buffering. So maximum speed at which my system can now operate is only 250 megahertz. Even though memory could operate at 400 megahertz. And this 250 megahertz is constrained because of the memory only now. Are you able to see this?
Yes, sir.
So what do we want to say? We tell the user, okay, see, we know the memory can operate at 2.5 nanoseconds and we need a duty cycle of 80%. But you don't worry. We will generate this internal duty cycle internally only. You don't worry about it. You operate at 400 megahertz. You keep an external duty cycle, which is at 50% only. So the external clock would be like this. Okay. But internally, my CKI would have a much longer high period. Does this make sense?
Yes, sir.
So that is also the reason why we need to generate the reset internally. Because if we were to use the external clock as the reset, then this constraint would set in.
Sir, this 2 nanosecond which you said, will it take 2 nanosecond every time, or because it depends on the reset, right? So the high time may change. Like if the
Why
bit
do
cell
you say, Moin, that it depends on the reset?
because reset is lowering that CKI, right?
Yeah, but reset will come only after. Okay, so when we will answer Anjit's other questions, we will see that. So reset or SAN will come only after my write detect has come. Is it not?
Yes, sir.
What does write detect depend on?
Detect. CKI.
Yeah, it depends upon the writing amount
On the
of time.
writing speed of my memory cell.
Yes.
You see? So all this is actually driven by the speed of the memory cell.
Actually, why I ask is some bit cell will be nearer to that decoded and some are far, right? So the time taken to this move these signals bit to bit may be different, I assume. So the
Could be different, yes. You're right. But you are assuming that all bit cells are symmetrical, exactly same. What if the cell which is closest to the IO is also slow? It could take more time than the cell which was farther away.
so the in the array all bit cells are not identical.
We talked about it in DVD also. No, you write your name 10 times, Moin. Will it be
Okay.
identical 10 times?
Yes, sir. Some difference will be there.
So the same thing would happen with thousands and millions of copies of the memory cells also, na? So you cannot deterministically say that the cell which is closer to the IO is also faster. So what do you need to do? When should the write detect signal come? When should the write detect signal come, everyone?
So when the write operation has been successfully done, when we have written into the bit cell.
Into any bit cell or all the bit cells?
So I mean, the one we are targeting, the address. Maybe.
So one address may have 32 bit cells. A one word could be 32 bit wide, na?
Yes, sir.
It has to be all the bits, sir.
It has to be all the bit cells. So what does this mean? That write detect should come after the worst case cell has also been written into. Are you able to see this?
So, but we would be writing at not only at the whole word, right? We would be writing only at a particular
Yeah.
bit
So
cell.
do you know which word has the worst case cell? I ask you to write your name 100 times, Raghav.
Yes, sir.
Can you tell me that 10th one will be the worst one?
No, sir.
The first one could be the worst one. 100th one could be the worst one.
Got it. Okay.
How much space do you need to leave for writing your name?
The worst bit cell, sir.
Otherwise, nahi aayega na?
Yes, sir.
So is this clear? And this also takes us to the question that Ranjit asked. Why? What is this reference word line and what is this reference bit line? See, the actual word into which I would be reading or writing may not be the worst word, or some bit of that word could be the worst bit. We do not know. So as memory designers, what we do is we add a reference word line and a reference bit line. Reference word line is very similar to the real word line. We will talk more about it later. And reference bit line is also very similar to the real bit line in terms of total capacitance. There is some modification we do, but that is what we will talk about later. And what we do is we ensure that the cells on the reference bit line and the reference word line ensure that they are the slowest ones through design somehow. We will talk about it. Okay. And that is what we use to generate the write detect. So they are kind of references. They ensure that worst case cell is also written into or worst case cell is also correctly read. That is why they are called reference word lines and reference word line and reference bit line. Does this answer your question, Ranjit?
Yes, sir. Sir, but here, if we look at the bit lines, so the reference bit line is much faster as compared to the bit line. So
yeah,
this doesn't ensure the required functionality, sir.
Yeah, look at it like this. After the write detect signal comes, how long does it take for the word line to get deselected?
Okay, it takes enough amount of time so that the clock.
So we have to keep that margin also into picture. We don't want to waste time.
Okay, yeah.
Moreover, this is just a cartoon.
Okay.
It is fairly representative, but it is still a cartoon. The exact correlation. So this is just a sequencing that I wanted to share with you.
Yes.
But the exact delay between two different signals, that would be different. This is not even representative of that. This is just a sequencing diagram.
Yes, sir. Okay.
Raghav, you have a question?
Yes, sir. So what is the word clock, I mean, signal does here?
This is write clock.
Yes, sir. So I mean, CK, I mean, the write operation will be controlled by this write clock.
The write driver is controlled by the write clock.
Okay, sir.
Don't worry, again, these are just nomenclatures. I've just used some name. So, any questions further? Any further questions? Because then I would want you to take you to the data sheet as to how a memory data sheet looks like.
I was not able to clearly understand the significance of the reset signal. I was able to get that we are resetting the memory to this original position, but exactly what crucial load it was playing, I was not able to get that.
Okay, you could understand that we wanted a duty cycle which is independent of the external clock.
Yes, sir. Yes, sir.
So how do you bring the clock to low? Internal clock to low. How do you create that duty cycle? You need some signals, no?
Okay. So sir, like initially I was getting the 50-50%, but based on my like reference word line, I generate that high period. I get the idea of that high period, how high the period should be. And based upon that, I select this reset signal, which will basically determining my that low period.
Yeah.
Okay. Okay, sir. Okay. Got it, sir.
So for every memory, the reset could come at a different time.
Yes, sir. And so one more thing, sir, are these reference word line, reference bit line, they are like actual bit lines in this memory array, in this memory structure.
Yeah. What else?
No, so because I was thinking that every bit line has that. So it would be, I was not able to structure that how exactly they would be part of that whole design.
So we will see how and where they are placed later. Don't worry.
Okay, sir. Okay, sir.
The 7th 8th lecture की मैं बात कर रहा था, that is when we will see this. Okay. Yeah. Anything else?
So the write detect is telling us the write operation has completed.
In the worst cell also. Or if you now generate the reset, then by the time word line gets deselected, write operation would be successfully completed everywhere.
Okay, sir.
Okay. So now that takes me to what we call as memory data sheet. What is a data sheet? What do you understand by the term data sheet? Have you seen a data sheet earlier?
Sir? Sir, why can't we use write detect as a reset signal, sir? Exactly. I mean, it does
what will you do during the read cycle?
Yeah. Okay, understood.
Yeah. What do you understand by the term data sheet? Have you seen data sheets of stuff of circuits earlier? What does a data sheet typically have?
Specifications of that device.
Specification of the device. What do you mean by the term specification, Animesh?
So all the data that a programmer or somebody who is working on it may need to make full use of that device.
May not necessarily be specification, but it is all the information. It may not be complete specification, that is, but it still has all the information so that someone can use it.
Yes.
So for a memory, what kind of information would you need to be able to use a memory?
Sir, it could be the operating voltage, the temperature, then total number of allowable read or writes, the capacity.
The right time. So the right time, the read time.
Yeah, the read and the write times, the typical minimum.
Okay. And
some also maybe like in the previous class we showed us that it could exist in different states. So maybe like that also.
Okay. Interesting.
Internal clock frequency.
Clock frequency. Okay.
Endurance.
SRAMs, unlimited endurance. Okay.
The
but yeah, flash ke liye you will need it. Yes.
So capacitance values, the maybe.
Very interesting. We just talked about it, that the input capacitance has to be within a particular limit. Yes. And
so size and PVD conditions.
Size and PVT conditions, very good. And
like pen description and all.
दोबारा से बोलो साची.
So pen description can be the part of the.
Okay, very good. So shall we look at one memory data sheet? Yeah, someone was saying something.
Speed, sir.
Yeah, frequency we talked about. Yeah, speed. We talked about read speed, write speed. Yes. एक part अभी आप भूल गए हैं. What do we talk about when we talk of circuits? Area. Someone said size. Yeah, area. Area is very important. Yes, and
Sir, figure of merit.
What do you mean by figure of merit?
Sir, noise margin values and.
What will a user do with that? But yeah, okay. Let us assume that for somewhere you will need SNR for a data sheet of a PLL, for example, or a ADC you will need SNR also. Yes, definitely.
Version, sir.
Version, okay. That is also important because as the version changes, timings and functionality may change. Yes.
Okay. Capacity.
Capacity, yes. Okay.
Leakage.
Power की terms में अब आ गए आप. Leakage, yes. And
The power consumption.
Power consumption, when?
It's in idle state or in like operating different.
Yeah, in all the various states, what is the kind of power consumption?
Yeah, and leakage also in the same.
So it should definitely talk about all the three at least. PPA, performance, power, and area. All three should be clearly evident in the data sheet. Okay, what else?
Supply voltage for operating this might be some load, how much load it can.
Okay, the load range and everything, yes.
The timing constraints. Timing constraints.
Timing constraints, yes. We talked about frequency and speed and everything, yes.
Technology node, which nanometer, 65 or 90?
Yes, which technology it is. So you should be looking at the right data sheet when you are designing something into your circuit. Yes. Very good. So shall we look at one data sheet? You've almost covered all of it, what we need to put there. So is it okay if we move to a data sheet now?
Yes, sir.
Okay. So this is a data sheet. This is from ST Microelectronics. They have very kindly allowed us to use it and for your purposes. So look at it. You talked about version, which version it is. It also talks about which date was it generated. The version may be 3.2 and the date. So that how old is this version? And you see, it also talks about something. 512 words, 774 bits. It says synchronous single port SRAM with 8 multiplexer inputs. So 512 cross 74 M8. And then there is also a prefix CMOS M55, which could be the term that they use for technology. ST, that ST is the one that developed. ST is the vendor for this particular memory. SPHD, single port, high density. LL typically could stand for low leakage, and so on. So the first page, you need to have at least this kind of information there. Then you see now, okay, so this is a memory data sheet in PDF format. But typically memory data sheet, when you will generate a memory instance, memory data sheet may be available in either PDF or HTML or text, or maybe all these kinds of formats. It will be made available to you when you purchase a memory from a vendor. It could be in any format, but what we are interested to look at over here is what are the typical details that are given in a data sheet, so that when we ourselves either become memory designers or want to become, system architects, whatever, and we want to use memories, what are the important things that we need to look at? Someone having done this course, MDT, should know at least this much, how to read a memory data sheet. Am I right? This is one of the most fundamental things that someone who has done this course should know. So we have this table of contents which talks about symbol and pin description. See, you never talked about pins. It also has pin description as to what kind of pins exist in the particular memory. And then we already talked about timing characteristics, power characteristics, leakage characteristics. So let's look at what it means one by one. So let us say we want to look at cell characteristics. So it says the number of words is 512, number of bits per word is 74. Number of multiplexer inputs is 8. What is this mux? We did not talk about it in the last class also. But what is this mux? What do you understand by mux? Anyone?
So you said for selection of column we use it.
For selection of column we use it, but I have a 512 cross 74 memory. So where does column come in? I have 74 bits. I want to read all the 74 bits. You simply accepted what I said. You did not question me.
We're reading 1 bit at a time, right? Not the complete word.
Why? You're not talking about a serial bus. The processor would need all the 64 or 74 bits from any location. Na? When you look at a processor, you say load address 5. So does it load only 1 bit of address 5? No, it loads all the 64 bits of address 5. No?
Sir, I asked same doubt last class. You said we will get that
Yeah, that is what I want to enter into. I'm
cycle.
just trying to see if you have the answer already or not.
Sir, to maintain the aspect ratio.
Maintain the aspect ratio. What do you mean by aspect ratio, Nikhil?
Number of word line in column and rows. We want to maintain number of word lines.
Yeah, why do you want to do that? You're right.
So
you're
that,
not wrong. I'm just
so
asking
that
why.
the delay reduces. Like if column is very high, so the bit lines will be large.
Sir, we want to make it a squarish memory.
We want to make it a squarish memory. Okay, why is it not a square memory, Abhi?
So words और bits ज़्यादा words ज़्यादा हैं bits कम है तो rows और columns या तो rows बढ़ जाएंगे columns बढ़ जाएंगे.
So what we are seeing is that the number of words is much more than the number of bits, huh?
Sure.
Okay.
Sir, the number of bits which 74 is that is the number of bit cells we have in the array, right? 74 bit cells we have in the array.
Yeah, 74 bits per word we have. Okay, so let me switch over to the whiteboard. Are you able to see my whiteboard?
Yes, sir.
Okay. So let us say we have this. Let us forget this 512 cross 74 for a moment. Let us say I just want to make a 64 cross 2 memory. I can want it. I can want a 64 cross 2 memory.
Yes, sir.
So what will I have? I will have a very tall memory where there are 2 bits per word and there are 64 such rows. And this is 2. Am I right? So what is the aspect ratio of this? 1:32. So अगर मेरा एक Have you seen pictographs of chips, ICs somewhere? Do you realize they are usually shown to be or designed to be squarish?
Yes, sir.
Now, what I'm saying is, in this squarish chip, make a memory which is aspect ratio 1:32. What would happen? Overall, this doesn't work now. If the chip is squarish, you would want something like a ratio which is manageable. Additionally, let us look as a memory designer only. Over here, my bit line has a capacitance of 64 rows. My word line has a capacitance of 2 columns. So the way the RC is distributed across word line and bit line is very skewed. In fact, my bit cell is very small. For write driver, I could actually have a big buffer. I can actually design a big buffer, but bit cell is bound to be very small because area is diamond in memories. So somewhere I could have a big driver. I do not have a capacitance to drive. But where I had a very small driver, the bit cell was very small, I have to drive this long capacitance of bit line there. So what would you want to do? You would say somehow, yeah, I can drive the word line faster. You say I can drive the word line faster, but please reduce bit line capacitance. So what do? You say, okay, let me fold the memory. So how do you fold the memory? You say, I will put 2 words per row. Instead of just 1 word per row, I will put 2 words per row. So what happens now if there are 2 words per row? How many rows do I have now?
32.
Half 32.
And how many columns do I have?
4.
How has my aspect ratio changed?
1:8.
And what do I now need to do? At a different level, what I now need to do is I just need to put a multiplexer here. है ना? That there will be 2 bits that would come. Of these 2 bits, depending on my address, one of the bits should go out. Are you able to see this? So that is why this is called as mux. Then let us say, oh, 1/1:8 is also a bad ratio. Can I do still better? So what do?
Sir, more folding.
I do, let us say, 1 more folding. I go for an additional fold and I say, okay, fold it once more. So now how many words do I have per row?
4.
4 words per row. How many columns?
16.
No.
8.
8. And how many rows?
16.
16. My aspect ratio has become 1:2. More manageable? Bitline capacitance has reduced by 1/4. Word line capacitance has increased to 4 times. And we call this as mux 4. Because there are 4 words per row. So what do you need to do? You need to bring 4 inputs, of which 1 would go out. Are you able to see this?
So I'm not able to understand the mux operation.
Okay, so now when you not understood the mux operation, very good. Thanks for asking. So let us say now I selected this particular word line. How many bits will be written into?
8 bits are there in a word
But
line.
I have only one address with me. I wanted to write only on 1 word. So which word will I write into?
Which word?
So I'm doing a write operation.
Yes,
when
sir.
I select the word line, 4 words get selected.
Yes, sir.
But I wanted to write only on 1 word.
So that will have to tell them na, okay, write in that.
Where do we tell them? How do we tell them?
through that mux.
Yeah, that is why you need the mux.
Okay. Okay. Yes, sir.
You got it?
Yes, sir. Yes, sir.
So
Yes.
so here only, like each word would have multiple bits, right? So for example, if I want to write on the like four word last word, like the fourth word, so each of these lines that you have said that it's mux 4, you have 4 lines. So each of these lines will be corresponding to all the 8 bits of that particular word.
No.
I mean all the bits of that. So because in each word we have multiple
So in
bits,
fact,
right?
there will be 2 muxes here. There will be another mux. This will be for the second bit.
Okay. So if we have, say, in a word we have 8 bits, so there will be 8 muxes here.
Yes.
And the number of mux will be depend on how many words in a particular row. And okay.
Yes, that is the mux size.
Okay. This 4 is
Sir,
represents that how many mux in a how many words for a particular row.
Yes.
Okay.
Sir,
Yes.
so the data sheet that you have shown us, that is 74 bits. But that the number of muxes were 8. Then what's the case in that? Like,
so over here there are 2 bits, but the mux is 4.
2 bits. So I'm not getting it. Like,
mux 4 means how many inputs per mux?
yes, sir. Yes, sir. Yeah.
And how many muxes? The number of bits.
Yes, sir. So here we have 8 bits. That's why we have 8
No.
muxes.
Here we have this. This is a 64x2 memory instance.
Okay. So we have 128 bits.
Total, yes.
Yeah. In a word line, we have 8 bits, like after the folding it twice.
Yes. After folding, we have 8 bits because mux 4 into 2 bits per word.
Yes, sir. Okay. So can you relate this with that 512 is to 74?
That's good. Let's do that. I think that will make it much easier for all of you. Let us say there is this memory which has 512 words and 74 bits. So now in that particular memory, they said we have mux 8. What that means is, first you do one folding, this becomes mux 2. Then you do next folding, this becomes mux 4. Then you do one more folding. And it would become mux 8. So how many rows would you have finally? 5 and 2 by 8. 64.
Yes. Yes, sir.
How many columns would you have? 74 into 8. What is that?
592.
596. So this memory would have 596 columns and 64 rows. Mux is 8. Columns is equal to 596. Rows is equal to 64. Words was already given as 5 and 2. Bits was 74. Is this clear?
मतलब sir, word per row is 512 divided by 8.
Words per row is 8.
Okay.
Sir, here still that it is not aspect ratio is not equal to 1 or it will not make it a squarish.
Yeah, so that is why I asked you, why do we only want to limit it to aspect ratio?
So, but we are using this mux, we are using more area for implementing the multiplexer also.
See, you do not yet have the sense of area in this system yet. I have not told you what is the X and Y of the memory cell. I have not told you what is the area consumed in the row decoder. I have not told you what is the area consumed in the IO region. So you cannot, just by looking at my cartoon, tell me that, okay, the area is more or less. You can't. Array area will anyway remain constant because the number of bit cells is constant. But overall memory area, how it will change, we can't say that just yet with the kind of information we have till now. Are you able to see this?
Yes.
Sir, so in this, there will be 8 mux and each mux will have 596 kind of lines coming to it.
No.
Sir, here we'll be having 74 mux and each of which is 8, each of mux will take 8.
Because there are 74 bits, I have 74 outputs to give. So there will be 74 muxes. Each mux will accept 8 inputs because each row has 8 words.
Yes, sir.
Is this clear? See, multiplexer is an important concept. You need to understand it well. Because if this is clear, I will go to the next step, which is called as bit interleaving.
So there will be 74 muxes and each mux will be 8:1.
Yes.
Okay. Okay.
Sir, here if we introduce mux, then the select lines for the mux will be based upon the address information that we give to the memory, and also the decoder size also might change based upon the folding which we do.
Yeah, obviously, because earlier you had to decode 512 words. So you needed 9 bits. Now you only need to decode 64. So you need only how many bits?
6.
6 bits. But you need 3 bits to decode the column address.
Yes.
So you still need all the 9 bits because your memory is 512 words.
Yes, sir.
But 6 bits for row decoding, 3 bits for column decoding.
Yes, sir.
Anything else?
So can you repeat about the capacitances you were saying about the word line and the bit line? How are they dependent if we like hold the memory and if the
You
memory
tell me.
remains constant?
Yeah, you tell me when there was no mux or when the mux was 1.
Okay.
Let us say per row, the bit line has a capacitance of CR. So what was the bit line capacitance?
So number of bits into CR.
Yeah, so to give me the capacitance number. How many rows are there if there is mux 1?
So in this 512. So 74.
Mux 1, number of rows.
Number of rows. Okay, rows 512.
512. So then the capacitance was
512
CR.
Okay.
What happens when the mux is 8?
64 CR.
64.
Okay. When we fold it.
Yeah. है ना?
Yeah,
it is only this long, otherwise it was this long.
Yeah, yes.
Now let us say per column, the word line capacitance is CC. So initially, mux 1 mein, what was the capacitance of the word line?
74 cc.
74 cc. What is the word line capacitance later?
596.
596 cc. So what have I done? I have reduced bit line capacitance and I have increased word line capacitance.
Word line capacitance, right? Okay.
Does this match with what I wanted to do earlier? I said I could actually have a bigger driver for word line. है ना? You remember I had said that word line driver could be much bigger than because bit cell is small, but word line I can have a bigger driver. That is what I have achieved now.
Yes, sir.
Yes, sir.
Is this part clear now?
Yes, sir.
So I have one thing to ask. Like in the data sheet, it was given 512 words and 74 bits. So the memory is actually designed like 512 rows and 74 bits in each row. Or with that 8 marks information, we can deduce that the memory is designed like this folded one.
So the mux in the data sheet was given to be 8, na?
Yes, sir.
So what would it mean?
कि फोल्ड किया है मतलब एक्चुअल में ऐसी ही डिजाइन है मेमोरी
64 क्रॉस 596 की तरह डिजाइन है
ओके ओके
है ना
सर 596 कैसे आ रहा है 74 into 8 कर रहे हैं ना हम तो 592 होना चाहिए उसमें
हाँ सॉरी 592 यस सॉरी
ठीक थैंक यू
सर कंटिन्यू फैजल क्वेश्चन डायरेक्टली ऐसा क्यों नहीं दिया है कि 64 एंड 592
डायरेक्टली ऐसा क्यों नहीं लिया है
मतलब डेटा शीट में ऐसा डायरेक्टली ऐसे क्यों नहीं है कि 64 इज द वर्ड लाइन
क्योंकि द प्रोसेसर वांटेड टू हैव 74 बिट्स पर वर्ड processor wanted 512 words to be addressed.
Yes, sir.
So I had to have 9 address bits, na?
Yes.
If I would say the memory is 64 cross 592, then the memory would become 64 words and 592 bits per word. That was not what the processor needed.
Yes, sir.
So here the mux concept comes in because we want to improve the performance, right?
We want to improve the aspect ratio. We want to improve the performance. We want to reduce, change the power, whatever.
So, but like it to me, it seems that it is coming at a very big area penalty because it does it. I mean, right in that because mux.
So I just told you that you do not know what is the area of the row decoder or what is the area of the IO. How can you estimate the area penalty here right away?
Okay. Yeah. Right. So. Okay.
Can you? Array area would remain same. Can all of you agree on that? Because the number of bits have not changed.
Yes,
Yes, sir. Yes.
So now, whether it is an area penalty or an area gain, you cannot know unless you know the row decoder area and unless you know the IO area.
Yes, sir.
Or can you imagine?
No, sir, not right now.
So cannot deduce that. Let us not jump into conclusions. We do not have the required information yet. I'm just making some cartoons for you.
Yeah. So and aspect ratio want to be squarish because it like fits into that kind of like packages.
Yes.
Squarish. Okay.
So even same number of rows and same number of columns does not mean aspect ratio is squarish. By the way, I have not told you about the aspect ratio of the memory cell in itself in the first place. Have I told you? Nahin na? So this logical aspect ratio that we were talking about, that does not really mean the physical aspect ratio is also a square. What if the bit cell is much taller than it is wider?
Okay.
Or vice versa?
Right, sir.
So again, don't read too much into the cartoons that we are making here. I would try to keep it as representative as possible, but even then, don't read too much into it. Shivam?
Sir, sorry, sir. I must not understand the point. Like you said, we need bigger driver for word lines, sir.
We
Why
can
do
make
we
bigger
need?
driver for word lines because they're not a part of the memory cell.
So they are external. That's why we need. We can make
We
them.
can
bigger.
make bigger. Yes.
Yes, sir. Thank you, sir.
Okay. Now let's go to the next level of complexity. यहाँ तक समझ में आ गया? Because if we have understood till here, then we take the next step on the ladder. Okay. So now let us consider this memory itself. What are we saying? There I want to make 74 muxes. So there are 74 muxes that I want to make because there are 74 bits, and each mux has 8 inputs. Am I right? So
Yes,
where
sir.
are those inputs coming from? There is one bit 0 coming from here, bit 0 coming, no, not here. Bit 0 coming from second word, bit 0 coming from third word, fourth word, and then 4 bit zeros coming from here. Are you able to see this? I just placed this one full word on this side. So there are 8 horizontal lines which are traveling to this particular mux. Are you able to see this?
Yes, sir.
Similarly, for the second bit, it would be another 8 lines coming from here. So how many horizontal lines are we talking about then? 592 horizontal lines. Are you able to see this?
Yes, so one for each bit.
One for each bit. Now, what does this mean? This means that every bit line is going to see such huge capacitance. See, horizontally it will run through the entire array, and then it will go to a mux. Is this a good way to design?
No, sir.
So what would you want to do? If you have to make a mux 4, what would be the ideal thing? That okay, all the 4 inputs linked to mux 4 are placed right here up there. Then for the next bit, all the 4 inputs should be right up there. That is what I want to do. So what does this mean? And this finally will give me bit 0. This will give me bit 1. This will give me bit 2. Let us say. So what does this mean? That if there are 4 words, then this particular word would represent word 0 bit 0, word 1 bit 0, word 2 bit 0, word 3 bit 0. Then word 0 bit 1, word 0 bit 2, word 0 bit 1, and word 3 bit 1. Then word 0 bit 2, word 1 bit 2, word 2 bit 2, word 3 bit 2. Are you able to see this? So instead of actually placing words as word 0, then word 1, then word 2, what am I doing? I'm actually interleaving. At every bit level, there is word 0, 1, 2, 3. Then at second bit, again 0, 1, 2, 3. 0, 1, 2, 3. What has it done? It has reduced this whole set of capacitances. It has, now I do not need as many wires. Just जहां पे bit line आई उसी को सीधा नीचे खींच के ले गए. We just pull it down, and right there we have the mux implementation done. Are you able to see this? So this is called as bit interleaving. Any questions?
Sir, I couldn't understand, sir. What is the difference between the two? The earlier that we were using. There also, sir, we were using those bits from the particular words.
Yeah, I wanted to use bit 0 from here, but the bit 0 for the second word would come from here, na, far away. For the third word, the bit would come from here, this region. Fourth word here, fifth word, sixth word, seventh word, eighth word. So I would have wires running all around my memory just to get the connections to one mux.
Yes, sir.
So this would lead to lots of congestion, lots of area wastage, lots of additional capacitances, power delay, everything.
Yes, sir.
So जो भी हम मक्स से अचीव करना चाह रहे थे कि मेमोरी की एस्पेक्ट रेशियो इंप्रूव होगी तो टाइमिंग इंप्रूव होगा, वो सब तो खराब हो जाता.
Okay, so we did this from keeping it like a square and selecting the bit lines
So
directly to
now
the
instead
mux.
of keeping all the bits of a word together,
Yes,
we
sir.
kept all the words of a bit together.
Yes, sir.
We changed it. Instead of all the bits of one word together, we kept all the words related to bit 0 together.
So how can we like do that? I mean, like we have different words and they are placed differently. How can we just cut a simple part and it just a bit size part and just place them
You are a designer, you
together?
can do that. Who stops you? What
Uh,
you need to do is wherever you write, you read only from there.
Okay.
है ना?
So actually, I couldn't understand.
For a
Yeah.
processor only needs to know what was written on this particular address. Where and how that bit was placed, the processor is not interested. Is it interested?
No, sir. It just needs data faster.
So all that I need to do is I need to write into this particular place only when I want to write a 0 bit.
Okay.
That's it. Are you able to see this? Any questions? So this, I know this is not a simple transition.
सर जस्ट फॉर क्लैरिफिकेशन, जैसे 512 वर्ड थे और हर एक वर्ड 8 बिट का था, तो हम हर एक वर्ड के फर्स्ट 0th बिट को हमने एक साथ ले लिया, 1th बिट को, 2nd बिट को, सबको 8 बिट को एक साथ ले लिया, सो दैट हमारा जो एक मल्टीप्लेक्सर है एक यूज करें तो हमें सिर्फ एक ही जगह से बिट 0 मिल जाए।
तो हमने क्या करा प्रिंस, हमने ये करा कि एक रो में अगर अभी मैंने यहाँ पे 4 वर्ड्स दिखाए, एक रो में अगर 4 वर्ड्स थे तो चारों वर्ड्स की बिट 0 को एक साथ रख दिया। अब let us say if it was mux 4, then what happens? We need to find a place for mux for word 4 also. Where would you place word 4 bit 0? So word 4 bit 0 would come here. Word 5 bit 0 would come here. Word 6 bit 0 would come here. Word 7 bit 0 would come here. Then again word 4 bit 1. Word 5 bit 1. Then word 6 bit 1. Then word 7 bit 1. Are you able to see this? Are you able to see the memory getting built, different rows of a memory getting built, and so on? So this is row 0. This is row 1.
Sir, what generates the select line for this multiplexer, sir?
Addressing. We gave 9-bit address. 3 bits will, in this particular mux 4 case, 2 bits will come to the mux.
Sir, the address which we get should also be in the same pattern, right? It should follow this pattern of bit interleaving.
Yeah, I will give address now. I will give address 0 and address 1 over here.
Yes, got it. Okay.
It will select. It will, no?
Yes, sir. Yeah.
Okay, anything else? So is bit interleaving clear?
सर ये वर्ड्स कैसे डेवलप हो रहे थे सर आपके, मतलब ये आपने जैसे दिखाया ये चीज सर, मतलब रो 1 रो 2 में, तो सर हमारा आपने एक मक्स में हमने 4 बिट सेलेक्ट कर लिए सबके 0 बिट, और फिर हमने एडिशनल वर्ड डाला तो वो उसके ऊपर ही सेट हो गया।
Yeah, Raghav, let us say we had a 8-word memory only. How many address bits did I have? 3 address bits.
Yes, sir.
So this is the complete memory. Let us say it was an 8-word 3-bit memory. Let us put it like that only. Okay. So let me just complete the memory here. Word 4 bit 2, word 5 bit 2, word 6 bit 2, word 7 bit 2. You want to see if this is really the case, huh? So I said mux 4 है, तो 2 addresses will go to decipher which mux, which column to select. यहाँ तक clear है? Is this clear till here?
सर वर्ड्स तो 8 हो गए, तो 3 हो गया ना हमारा ऐप यहाँ पे.
नहीं, बट एक कॉलम में तो 4 ही वर्ड्स है ना.
Yes sir, yeah, okay sir.
Now which word to select? I still need to identify decipher the third address bit. This goes to the row decoder. If A2 is 0, row 0 will be selected. If A2 is 1, 1 will be selected. Do you see that finally one word will be selected?
Yes sir. So but
by a cross section, by selecting a cross section of word line and bit line, I would have decoded the entire address bus. Is it clear?
So but word, for example, in the first mark, word 0 और word 4 में किसकी bit 0 select होगी, वो कैसे मैं distinguish करूँगा कि मैं 4 आ रहे हैं?
By selecting the appropriate word line.
Okay, ठीक है, yes yes. हाँ yes sir, got it sir.
Now I'm using at a cross section of bitline and word line selection. Whatever word is there, that is what will be get selected.
Yes sir, got it sir. Thank you sir.
है ना?
Yes sir.
Clear to everyone? Any questions?
Sir, earlier, sir, we were folding the memory array so that and all the bits of a particular word were put all together. So, sir, how can we arrange the structure to have this kind of design?
We just decided to arrange it like this so that our capacitances will reduce. How to करके तो दिखा दिया. We did it, just did it. It is our choice. We are the designers. नहीं? See, if we would go by what we had initially logically thought, we saw there is a big problem there. है ना? There's this big problem of all these capacitances that was coming into picture.
Yes, sir.
है ना? कौन से कलर से करूं? ग्रीन से कर देता हूं. चलो. All these capacitances were coming into picture. We didn't want to have all this trouble with us. Are you able to see this? So we said, okay, let us arrange the things differently. And we arranged it differently. We interleaved the bits. Can I not do it? Has anyone stopped me from doing this? Okay. So, is this clear? Can be done like this? Any questions? Because I still want to spend 5 minutes on the data sheet. Yeah, Shivam.
Sir, yeah, we can do this kind of, we can make memories like this. But sir, what I wanted to ask, like, sir, what structural arrangements we can do to have this kind of structure?
You don't need to do anything. You just design a mux like this, where the bits are where the inputs are coming from vertically up there, not from sides. That's it.
Okay.
It is so seamless.
Yes, sir.
So if you would do this course, the creativity course that I'm teaching this semester, you will see that this principle is called the principle of geometry or spheroidality or stuff like that. You just rearrange the material in such a way that it becomes simpler to handle. You may want to, so regarding that principle, inventive principle, there is also this Mobius ribbon that you may want to see. Very interesting geometrical transformations can happen, which can really ease out your life in a very significant way. Just like it has done over here.
Yes, sir.
So that is the concept of mux and bit interleaving there. Okay. Now let us look at the data sheet again. We can. So what was there in the data sheet? Let us look at that. So we said there would be 64 columns, 64 rows and 592 columns. You see this part? 64
Yes,
and
sir.
592
Yes,
columns.
Yes.
Aspect ratio, they said something. And now you see width is 837, height is something. And it also has the thing of area and perimeter given there in the cell parameters. Are you able to see this? Aage badhe? So once you have that, then you also have a symbol view. So that whenever, because we said that the data sheet should have sufficient information for us to be able to design or understand the complexity of the design there. So this symbol view tells me what all pins do I need to route, what kind of congestion should I expect around this particular memory. And then you will see we also give pin description. What does each pin do? What is the functionality of each pin? What is the capacitance of that particular pin in this particular memory instance? You see, clock already has a capacitance of 30 femtofarads, and compare it with capacitance of other pins. All other pins have much lower capacitance. You see, address pins 8 femtofarads, control chip select 7 femtofarads, write enable 6 femtofarads, and clock we're talking of 30 femtofarads. Are you able to see why we could not use external clock for all the other purposes? The discussion that we had just before sharing the data sheet. Clock already has high capacitance. We cannot load it any further. And then there are these pins like sleep, and then there are these additional pins, which are scan chain related. So you see, memory has a scan chain of its own. There are so many inputs in this particular memory. If you look at it, how many inputs do we have? 1, 2, 3 plus 9, 12 plus 74, 86, 87, 88, 89, 89 यहाँ तक कर लिया था, 90 plus 74 कितना? 164 pins for one memory instance. Compare it with a NAND gate. 3 input NAND gate has 4 pins. A flip-flop, 7 or 8 pins. Memory has 164 pins. And this is not the biggest memory. A bigger memory would have many more pins there. So if you have so many pins there, you would rather have a scan chain internal to the memory. It's a big macro. So we also have a scan chain dedicated to the memory there. And then we have timing characteristics. Cycle time, what is the highest frequency, CK high pulse width, CK low pulse width, access time, data valid after write, after clock, and so on. So all the pins, there could be some timings, CSN setup time, CSN hold time, address setup time, address hold time, and so on. There are symbols linked to all these timings, and we also are putting some number as min or max. What do you mean? What do you think this min and max would mean?
So setup hold kind of thing.
Yeah, min would mean that at least this much timing should be maintained. Max means this is the maximum it would take.
It's a pessimistic approach.
Yes. That
Yes.
this is the safest, or because if you would latch the outputs before this max timing, then we are not guaranteeing anything. But after this timing, if you latch, we guarantee everything.
Yes.
Sir?
Yes.
Sir, I have seen in 3-4 positions, sir, process is given as best, sir.
Okay.
In this paper itself. What do you mean by best, sir, exactly? Over here, even in the second slide.
Yeah, so we saw about best process, worst case process, everything we saw now in DVD
Okay.
also.
corresponding to memory, which
Best
one?
case means best
stands
case
for the
process
best
meant
case.
fast NMOS, fast PMOS.
Okay.
है ना? Best case process meant fast NMOS, fast PMOS. And you see there are timing diagrams also.
Okay.
See, we had these symbols over here, timing symbols, TA, TS, TAS and everything. Now they're also shown in form of timing diagram. What does TAS mean? What does TAA mean? And so on. Okay, so these timing diagrams are also there in the data sheet so that you can actually understand what different timings mean, what various constraints linked to different timings mean. Okay, and then you will see we also give the power numbers. See, power active power. So first is the peak current, then power active read 50% of self toggling. So you can see the definitions of what each of these symbols mean right here in the notes section also. So we give the dynamic power numbers in the data sheet. And finally, we also give all the leakage numbers in the data sheet. We're also giving the tolerances. Leakages are valid at plus minus 10% because they can vary on input and output states and so on. So all the information that a user needs to decide whether I want to use this memory or not, we want to give in the data sheet. So what I will do is I will upload this data sheet in the classroom. I would want you to spend some time understanding it. Okay. If you have any questions, you can ask in the classroom itself. The TA will help you respond there.
What is scan?
I'm sorry.
What is scan?
What is?
Scan chain. Scan chain. You're showing that.
Scan.
Scan chain.
Can you just write that in the chat window? I'm not able to understand what you're
He's
saying.
asking what is scan chain.
Yeah, scan chain. Scan chains are test structures. So you will study about them more in the VDF course also. But you can find that online also. Scan chains are test structures
for testability,
which are embedded in the design so that the design becomes testable. Okay, so they are linked to testability of the design. Does that answer your question?
Okay, so I'll look into it.
Yeah.
Hello, sir.
Yes.
Sir, here in this datasheet, we can see that the sleep pin is having a very much higher capacitance. What is the reason behind it?
Because sleep, okay, so what happens? Clock, you need to toggle every cycle. So for clock,
yes,
you have timing constraints which do not allow very large capacitance to be put on the clock pin. Okay. Sleep pin, on the other hand, would toggle after every 100 cycles, let us say. Because it shuts down the memory. It plays with the power rails of the memory. So the sleep pin, you cannot toggle every cycle. So you say, okay, for the sleep pin, because I'm not toggling it in every cycle, I can relax the capacitance constraint a bit. Don't waste area buffering the sleep pin. Take the sleep pin directly to wherever you want to. It will be slow, fine, no problems. It will still be okay with us. Is that okay?
Okay, sir. Yes, sir.
So, but for all other pins, you will see that there is a limit on what kind of capacitance it has. Okay. Anything else? Yes, Raghav.
सर एक थोड़ा लाइक बेसिक क्वेश्चन था सर, ये जो अभी SRAM की डेट कोई SRAM वाली मेमोरी का डेटा शीट है ना, राइट? ये सर सर लाइक SRAM है तो सर ये मतलब ऑन चिप मेमोरी होगी हमारी चिप,
ये एम्बेडेड SRAM है, यस।
सो सर लाइक इसमें मतलब जब हमारा चिप का पार्ट है, सो इट इज अ पार्ट ऑफ द सेम सिलिकॉन। सो सर इसमें जो पिन्स होती हैं उसको हम कैसे लाइक विजुलाइज करते हैं कि पिन्स मतलब कैसे आप डिफरेंट आईपी कैसे कनेक्ट हो रहे होंगे उस मतलब
आप बताओ, आपने स्टैंडर्ड सेल्स बनाए कैसे बनाई थी उनमें पिन्स?
सब मेटल से बनाई थी।
यहाँ भी मेटल से बनेंगी. They will be routed by metal. So pins in memory are typically made in metal 2 and metal 3. In advanced technologies where the number of pins is still higher, you could make some pins in metal 2 and metal 3, some pins in metal 3 and metal 4 to reduce the congestion, because there are so many pins there.
Okay, so sir, like if अगर मेरी मेमोरी की complexity बढ़ती जाएगी तो मेरी जो metal layers हैं वो बढ़ती जाएंगी ऊपर जो structure है ऊपर वाला.
There is no other option. If I have to get more density, then I have to, otherwise pins will start to define the area that my memory has.
Yes sir. Okay. Okay sir. And sir वो आपके office hour का शायद से रह गया था, आप बता दीजिए.
Yeah, we have not discussed about the office hours. So let me talk to the TS once and let me come back to you with all the office hours for all of us.
Okay, sure sir. Thank you.
Okay, we'll post that in the classroom itself.
Okay sir.
Thank you for reminding, Raghav.
Okay, thank you sir.
Yeah. Anything else?
हेलो सर.
Yes, Rohit.
सर यहाँ पर जब डेटा शीट में कुछ क्लॉक्स के मतलब कुछ पिंस के लिए स्टेट्स दिए हुए हैं और कुछ पिंस के लिए स्टेट्स नहीं दिए हैं, तो मतलब वो एक्टिव हाई या एक्टिव लो है, हम मतलब ये
like
कैसे
some pins
पता
are
करते?
output pins and some pins are data pins. Can there be a default state or a preferred state for a data pin? No. है ना? SCTRI मतलब control. So scan chain input for control bits. So it's an input pin. It is data. It will carry some information. है ना? So that could be 0 and that could be 1. And there's nothing about active high or active low on here. So control signals, control pins would have a preferred state. Look at this. Control pins would have the preferred state. There is a preferred state for CSN. The memory is active when CSN is low. WN, memory is in write mode when it is low. But address, can there be a preferred state for address? No. Address is data, address is information. है ना? It's not a control pin, it's an input pin. Is that clear, Rohit?
हाँ, yes sir.
Okay. Anything else?
सर एक और चीज थी सर, इसमें जैसे अभी यहाँ पे CK लिख रखा है, यहाँ पे लिखा है एक्सटर्नल क्लॉक इनपुट फॉर द मेमोरी. सो सर जैसे कि हमारा अगर मान लीजिए टोटल पूरे चिप है तो उसमें हमारा एक सॉर्ट ऑफ स्टैंडर्ड सेल रीजन है, हमारा डिफरेंट मैक्रोज हैं, तो मेमोरी का भी एक डिफरेंट मैक्रो हो गया हमारा. तो सर इज इट ट्राइंग टू से दैट कि हमारा जो मेमोरी है उसके लिए सेपरेट पिन होगी एक्सटर्नल से लिंक करती हुई, एंड जो हमारा दूसरा मैक्रो है लॉजिकल है उसके लिए डिफरेंट होगी?
No. That simply says memory के external input है ये.
Okay.
जैसे flip flop है, flip flop की भी CK pin होती है, वो भी उसको there could be a flip flop is so small a circuit you may not have an internal clock, though you have internal clock in the flip flop also, but you can say that CK is the clock input for the memory. You can avoid they could have avoided the use of term external over here.
Okay. एंड सर जैसे हमारा जो पूरा लॉजिक, जैसे हम केवल मेमोरी को वैसे देखें स्टैंडर्ड सेल्स एंड डिफरेंट रीजन्स, तो सर हमारे उसमें CTS यूज करते हैं फॉर द क्लाउड राउटिंग इंटर, तो सर मेमोरी में भी सिमिलर काइंड ऑफ स्टेप यूज होता है?
या मेमोरी के अंदर नहीं, बट मेमोरी को कनेक्ट करने के लिए द रेगुलर CTS विल बी यूज्ड. क्लॉक ट्री सिंथेसिस विल कनेक्ट द मेमोरी इनपुट आल्सो.
ओके. और सर जो आप बोले थे कि इंटरनल क्लॉक जनरेट करते हैं मेमोरी के अंदर, उस स्टेप को क्या बोलेंगे हम, मतलब उस स्टेप की जनरेशन को?
That is internal to memory. Data sheet से उसका कोई लेना देना नहीं है.
Sir,
we talked about it. We in the cartoon that I showed you, I had used the term clock generation, internal clock generator.
Yes sir. Okay, so that is a separate kind of block itself.
Yeah.
Logical circuitry है.
Yeah.
Okay sir.
It's not a buffer. It's a clock generator.
Okay. Okay sir.
Otherwise, I have simply said, you could have said clock buffer, no? No, it's not a buffer. It's a clock generator. Okay.
Okay sir.
Yeah. So we'll close the class now.
सर कैश मेमोरी का भी डेटा शीट यही होगा या अलग से सेपरेट होगा?
Yeah, typically same memories would also be used for cache purposes.
उसके लिए कुछ एडिशनल इंफॉर्मेशन चाहिए शायद ना, लाइक
कैश सबसिस्टम की इंफॉर्मेशन होती है, that we will talk about later when we will talk about caches. Okay. So okay friends, thank you, all the best. We have already exceeded the class time quite a bit, so thank you, all the best. See you on Thursday now. Bye bye.
Thank you, sir.
Thank you, sir.